Hey there, physicists. We're going to learn about drag force and terminal velocity today. This is Mr. Clegg. So drag force is sometimes written with the notation FD, and it's sometimes written with, and sometimes we use air resistance like FR. And they're basically the same thing, except that drag force can be in a liquid like water or oil or even honey. Very big drag force in honey. Air resistance is, just in air, obviously, but it's the force that is acted upon an object when it's moving through the substance, moving through water, moving through whatever. All right. So the best way to test this, we'll learn about terminal velocity a little bit later in the video, but the best way to test this is to put it in a wind tunnel. If you have a wind tunnel, it's a very good way to measure this. It's a very precise and accurate way to measure it. So you have a thing like, let's say you're testing parachute, and put that in the wind tunnel. You have a force scale, so that measures how much force is being put on the thing by the wind. And then you can control the speed of the wind by using the wind tunnel motors to control that. And so what people found when they did this experiment was that the force depended on the area. And I'm not talking about the surface area of the parachute. So, imagine that you were going to try to catch butterflies in a net or something. It wouldn't matter how, if you had a net that shape, or if you had a net that was a little deeper, or if you had a net that was really deep, the same number of butterflies would go into your net either way. And in fact, the longer net in that case would catch more butterflies. I'm not proving my point very much, but the same amount of butterflies would go through this opening. So that's how many you would catch. But the reason why they make butterfly nets longer is because you're more likely to keep the butterfly in there and not have it come out. Hopefully that was clear. So it doesn't really matter how deep your parachute is. Most parachutes are kind of rounded like that, so you can have a certain stability. So it's for stability, but the actual drag force only depends on the area. So if you make a parachute really flat, it just flaps around like a leaf, and it doesn't really work very well. So you got to make parachutes a little longer, but really it's only the width of the parachute. In other words, the area. It's the diameter and therefore the area that matters to your drag force. So you can graph it, area down here, drag force up here. You get a direct linear relationship, as we know from our study of mathematical relationships. So here we have a direct linear relationship. And when they studied the speed of the wind versus the force, they found out it kind of made a curve like this, and that is quadratic, as we know. All right. So they did some experiment. They fit a curve through their data and found it like that. So one of the cool things is when you have two different relationships, just like when we had in Newton's second law, we had the acceleration versus net force, and it made a line. We had the acceleration versus mass, and it made a curve like that. And we put those two things together into one thing, Newton's second law. Well, here's the way they could put these two things into just one thing. So we have the drag force here, that's it's proportional to the area, and then it's the speed squared. And the proportionality constant in this case for a parachute in air is approximately 1.075 kilograms per cubic meter. And those units don't really mean much except to just make sure that the units of all the other things work out, like Newton's meters squared and meters per second, all that squared. And so there you have your drag equation. All right, so that's pretty cool. Sometimes you'll see this K as different things. I put them all together just to keep things a little simpler for here. And so now we're going to talk about terminal velocity. Terminal velocity is the constant speed that something falls at once it's got going really fast, and the drag force keeps it going just at a constant speed, so it's not speeding up anymore. So when you first drop a rock off a cliff, let's say, here's you, and you drop, that's a horrible you. Okay, anyway, you drop the rock off the cliff, and at first it starts to speed up, right? And it continues accelerating because gravity keeps pulling on it. And at a certain point, though, the air drag won't let it speed up anymore. And here's how that looks. So here's our rock, and here's the free body diagram. When you first start, you have weight only. As soon as you let it go, you're not holding it anymore. There's just the weight. There's no air drag yet. But as it speeds up, there gets to be a little bit of air drag because, as you saw, air drag depends on the speed of the, right? Air drag depends on, in fact, the square of the speed. So as it speeds up, air drag increases, and it increases, right? It keeps increasing. I want to try to make that straight. So it keeps increasing, and it keeps increasing until it becomes equal to the weight. And as soon as they're equal, you have no net force, and therefore you have no acceleration. So therefore, what? Does it stop? No. When it has no acceleration, could be stopped, but in this case, it's not. It's moving at a constant speed. So the terminal velocity, called VT, is a constant speed, right? So it's falling at a constant speed. And you've probably seen that when you drop a piece of paper like this, it floats down pretty slowly, and a parachute floats down pretty slowly. Something like a rock has a much higher terminal velocity, and we might be wondering, well, why is that? Well, because the drag force, right? The drag force depends on the area. So if you have a big, wide area like a parachute, your drag force is going to be a lot. So it doesn't have to go as fast to have a pretty big drag force. And so it can float down slowly. If you have a very small thing like a rock, the drag force isn't as much until you get going really fast, and then you have a lot of drag force. So then you're going to have a higher terminal velocity. Everything has a terminal velocity. Okay, so if we want to figure out the terminal velocity of our parachute, we could actually, before we actually figure it out, we have to do one thing. So when we have a parachute, we don't really know what the drag force is, but we do know what the weight of the whole parachute and the mass that we attach to the system is, right? So if we measure our the mass of our whole parachute system here, okay, there's our parachute, and here's our mass attached to it, the mass of this whole thing, the whole system. All right, so let's just say we measured the mass, and it's just make up a number. Let's say it's 55 grams. We want to know what the weight is. Okay, so let's turn that into kilograms. So we have to turn that into kilograms first, and then we can turn into weight. So remember that Fg, the weight, is equal to m times g. So we're going to multiply the mass in kilograms, 0.055 kilograms, times 9.8 meters per second squared. And then we'll have the weight. And that comes out to be 0.539 newtons. Okay, so that's the weight. Now the cool thing is, when we're at terminal velocity, the weight and the drag force are actually the same. So I can rewrite this equation in a slightly different way. I can write it like this. Since Fg equals Fd at the terminal velocity, then I can rewrite it like this. Fg equals Ka Vt squared. So that's the terminal velocity squared. So in this case, I know what the weight is because I just figured it out. I know what K is because it's up there. See, it's way up here. 1.075. That's just a constant. That's true for any parachute. And then I have the area. So I need to get the area, and then I'll be able to solve this for my velocity. So let's just do the area real quick. Let's just say that, so the area is pi r squared for a circle. Maybe you had a rectangular parachute, in which case you would measure it like this, length times the width. right? Remember, we're measuring the size of our parachute kind of in a horizontal plane as it's falling. We don't care how tall the parachute is, we just care how wide it is in every direction, right? So if you have a round one, even if it comes up like this, doesn't really matter. We're just measuring the area of the circle down here. We don't care about how tall it is. Okay, so I measured my parachute and it came out to be 50 centimeters. And that's equal to 0.50 meters. So that means that my radius is half of that. That's 0.25 meters. And so I'm going to say that my area is equal to pi r squared. So that's going to be 0.25 squared, meters squared. And that comes out to be, hold on a sec. That comes out to be 0.196. I'll just round it, I guess. Meters squared. So there's my area. Now I have all the things I need to find my terminal velocity. And the first thing I'm going to do, though, I'm going to actually rearrange this so I can have my little equation for terminal velocity. So I'm going to take that and I'm going to actually just divide by k and a at the same time on both sides. So it's going to end up on the other side. So I'll have my fg over ka, and that's going to be equal to v squared, t squared, terminal velocity squared. I'm going to switch sides and I'm going to take the square root of both sides at the same time. All right, I'm going to take the square root. I know that this could be negative, but I don't care about the negative, so I'm just going to call it fg over ka. And I need to make my square root sign a little longer so it covers the whole thing. There we go. That looks a little funny. Yikes. Anyway, I think you can see that. So there's my actual equation for terminal velocity. And one of the things you'll notice is that the weight makes the terminal velocity faster. And this is, I think, one of the reasons why people think that heavier things fall faster. They do fall faster when you have air resistance because your terminal velocity is faster for a heavier object. But if you have a bigger, wider object, that's in the denominator, so that makes your terminal velocity slower. All right, so that's just kind of interesting stuff there. Now, if we were going to figure out the terminal velocity in my example, we just have to plug in those numbers that I got. So let's do it. So let's do the terminal velocity in my example. Okay, let's put in, oh man, there we go. Okay, the force of gravity, the weight, and then I already figured out 0.539. So I'm going to put 0.539. We really should be putting units in here. So I'm going to go ahead and do that. I'll put newtons in there. Sometimes I don't do that in class because I don't want to make things look too complicated, but really it's better to put the units in. Down on the bottom, we have our K. That is 1.075. So we have that there, 1.075 kilograms per meter cubed, which is kind of weird because it seems like a density unit, but it's not. It's just a constant. And then we have our area, which is 0.196 meters squared. Need to make everything a little longer up here. There we go. And now all we have to do is pick up a calculator. I'll do this one with you on screen here just because I think it can be a little complicated. So we're going to clear our calculator. We're going to start by just typing in the numbers inside. So we're going to put 0.539, and then we're going to hit divided by 1.075. We're going to hit divided by again, and we're going to put 0.196 and hit equals. That's the whole inside part. It gives me like 2.558 something or other. And then I'm going to hit the square root key. And I get my answer, which is 1.599. Go ahead and leave it at that for now. And that should be meters per second. There's actually a way to go through and make sure the units all cancel out, but I'll leave it off this video. So that's my thing. I could probably round that. Let's just round that to, let's just say that's about 1.6 meters per second. So that's the theoretical terminal velocity of my parachute. All right, guys. Hope this was helpful. Ask me if you have any questions. See ya.